Okay, so today we are going to explore the idea of arc length. In other terms, if I have this function here, how do I find the length of the curve from A to B? What is its length? Now we're going to do this with integrals, so we're thinking about adding up an infinite amount of something. And we've done a lot with this kind of function and things. We've taken this region here, broke it up into equally spaced subintervals. We've used those subintervals to help us calculate things like area. We can calculate the area a few different ways, if you remember. Basically, one of the things that we did, this is kind of like just a review, but one of the things we did is we used what's called a Riemann sum to estimate the area. And those Riemann sums were basically adding up rectangles. And we could use the right side method, the left side method, or the midpoint method to figure out the different heights of those rectangles. And then we could calculate base times height for each one and add them all together. And if I was going to draw for you what those, let's just say we choose the left side method. What I would do is I'd use the left side of every subinterval, and I'd draw across to the other side of that interval, and that's how I would create the height of every one of those rectangles. And actually what we're going to do for the length problem is that we're going to create a little triangle on the top of every single one of these rectangles. And those triangles, first of all, because they're perpendicular, those legs, we know that those are right triangles. And we know that the horizontal leg is going to represent some small change in x, so we can call that horizontal leg x. And the vertical leg, as I go from rectangle to rectangle, is going to be some change in y. And if I stacked an infinite amount of these rectangles, it would be dy, or a very small change in y. And what we're going to do to figure out the length is we're going to add up an infinite amount of these hypotenuses. And because I have a right triangle here, the hypotenuse formula is simply going to come from Pythagorean theorem. And so when I go and I start thinking about the length problem, what I'm going to do is I'm going to add up an infinite amount of these hypotenuses. And this formula here is incomplete in its current form, but it gives us a starting point, and we can finish it algebraically depending on what kind of function we're working with. And I'll show you some examples in just a second. The idea here is that the integral allows us to add up an infinite amount of something, and the infinite amount of things that we are going to add up, in this case for length, is hypotenuses. And so we have this formula just as our starting point. Now, depending on what the function says will depend on how we adjust this formula. So let's see here. If I start with my formula coming from the Pythagorean's theorem here, I'm going to have my square root of dx squared plus dy squared. And if my formula is, if the function I'm working with is in the form of y equals some function of x, and when I take the derivative of that, I would get dy over dx. And so in my formula here, I'm going to want to see dy over dx. So in order to do that, I'm going to divide each thing here by dx. And to put it underneath the square root sign, I guess technically I'm dividing by the square root of dx squared. To keep the system balanced, I'm going to then multiply by the square root of dx squared, which everybody knows the square root of dx squared as I move from right to left is just going to be dx itself. That means I'm going to also be using x bounds. Okay? If the function that I'm working with was written differently, instead of y equals some function of x, if the function that I'm working with is written more as x equals a function of y, then I can adjust to this formula a little bit differently, kind of using the same algebraic concepts though. So I have my starting point where length is going to equal the sum of an infinite amount of hypotenuses. So it's the square root of dx squared plus dy squared. But my function this time is x equals some function of y. When I take the derivative of that x, I would have dx over dy. And that's what I want to see in my function that I'm working with, my starting point. And so I would divide everything by the square root of dy squared, and then to balance it out, I would multiply by the square root of dy squared, and then I would have to make sure that my bounds are y bounds this time and not x bounds. And again, we kind of just look at how the function is described to us. Is it a function of x or is it a function of y? When I take the derivative, do I get dy over dx or do I get dx over dy? And those are the things you want to see in your length formula. So let's actually do a problem here. This problem will come right out of your book. It is example 1, I think, in your book. It's y equals x to the 3/2 power, and it's going to go from the point 1, 1 to the point 2 and 2 square roots of 2. I know I wrote it wrong, but that y value is technically 2 square roots of 2. Okay, let's keep moving. So first thing we need to do is kind of draw the picture here and try to understand exactly what's going on. And you could graph this a bunch of different ways. I'll just kind of tell you how it looks. Y equals x to the 3/2 kind of has this parabolic shape. And we're going to try to find the length of this curve from x equals 1 to x equals 2 along that curve. So let's come up with our starting point here. My starting point is that this length is equal to an integral of the square root of dx squared plus dy squared. I want to start to think about how I'm going to adjust this formula. And so I go back to the way the function is described. And the function is described as y equals a function of x. When I take its derivative, I'm going to get dy over dx. And you can see that dy over dx is 2/3 x to the 1/2. And that way I'm going to adjust this formula that way. I want to see the dy over dx. So I'll divide everything by the square root of dx squared, balance it out by multiplying by dx itself, and make sure that I have x bounds. Now when we actually start to do the calculation, what we realize is that dx squared over dx squared is simply 1. dy squared over dx squared is simply the derivative in this case, 2/3 x to the 1/2 squared, and my bounds are going to be the x coordinates of the points that I'm using. In this case, x equals 1 to 2. Integrating this, probably a calculator-based problem, is then going to represent the length of the curve from one point to the next. Now let's kind of think about this a little bit differently. Let me give you the same basic shape here. However, I'm going to describe the function differently. Instead of y equals x to the 3/2, I'm going to solve that for x, and I'm going to say that x equals y to the 2/3. And we're going to use the same point, 1, 1, and 2 square roots of 2, to find the length between those 2 points. A quick graphical representation of what's going on. Let me draw my axis here. And we remember that this function is slightly parabolic. And we can go ahead and label a point that we're finding from one to the next. And we're going to find the length of that curve by adding up an infinite amount of hypotenuses together. So when I start to establish this integral, we know we have our starting point, which is the sum of these hypotenuses. The hypotenuse is coming from the Pythagorean theorem. And if I look back at the function and how it's described to me, what I realize is that the function is x equals some function of y. And so when I take its derivative, I would get dx over dy. And quickly I could do that. That's 2/3 y to the negative 1/3. But I want to see dx over dy in this formula. And so what I would do is I would divide everything by the square root of dy squared. And to balance the function, I would then multiply by dy itself. And I would have to make sure that this time my bounds are y bounds. So when I actually start to compute this problem, I'm going to have the definite integral, and this time dx over dy squared is going to be 2/3 y to the negative 1/3. Oops, I'm thinking faster than my computer. Hold on a minute. So dx over dy quantity squared is 2/3 y to the 1/3 quantity squared, plus dy squared over dy squared is 1 times dy. And this time I'm going to use y bounds, and my y bounds are going to be from 1 to 2 square roots of 2. And if I calculate that value, again, that value would represent the length of the curve from one point to the next. As you look at this, you should realize, and maybe you should calculate these on your own, but these should be the exact same number. We were just thinking about how to define them slightly different.